Start recording. Go full screen. Okay, this is Physics 1B for September the 8th, is the first hour. And today we're going to be finishing up our discussion of statics, which means we're going to be talking about Archimedes Principle, buoyancy, the idea of how things float. We'll look at objects that are fully submerged, so like they're fully underwater. We'll look at objects that are partially submerged. And then we'll talk about gauge pressure and barometers and how barometers work, what a barometer is. And then if we have time, which I think we should, we'll start talking about fluid dynamics, which is fluids that are moving. So that's going to be like fluids flowing through pipes. And we will start talking about the two kind of ideas that we're going to use to look at fluids that are moving, which are the continuity equation and Bernoulli's equation. Bernoulli's equation is something that helps us understand how a lot of things work, but in particular, it helps to explain like how an airplane flies, and it also explains some other phenomenon that you may have experienced before that we'll discuss at that time. All right, so let's get started. So buoyancy. So buoyancy is a force, right, that's exerted on an object whenever it's placed into a fluid. Just to summarize what we did last time, the idea is that if I have a fluid that's contained in some kind of a vessel, so let's say we have water. If I have an object that is submerged in this fluid, so if I have an object here, and let's say it has a volume that I call VO, the O stands for object, and it's submerged completely within a fluid, then there are going to be forces acting on this object. Obviously, there's going to be a weight that acts on the object that pulls down like this, but there's also going to be a buoyant force that acts on the object that points up like this. And what we derived at the end of class last time is that that buoyant force is equal to, and you could figure it out directly from what Archimedes' principle says. Let's read it again. It says, when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. So how much fluid is displaced by the object? And it's the weight of the fluid displaced, right? Well, the object has a volume that's VO. And if I take a volume and I multiply by the density of water, so right here I'm going to write rho F, where the F stands for fluid. In this case, it's water. So the density of the fluid times the volume of the object. If I just multiply those two by each other, what does that give me? When I take density times volume, what do I get? What do you get when you take the density of something and you multiply by volume? What is that? Mass. Yep, that's right, mass. So this is mass. So what we need is the weight of the fluid displaced by the body. In this case, the weight of the water displaced by the body. So we've got the mass. This is going to be the mass of the water, right? Mass of the water. So then what do we need to multiply this by to get the weight of the water? We have mass. So we multiply by what to get the weight of the water? Gravity. Yep, G. And that gives us the weight of the water displaced, right? Because it's the volume of the object times the density of the fluid. This gives you the mass of the water. So it'd be like, suppose you take this object and replace it with water. That's how much it would weigh, right? And that's the buoyant force acting on the object when it's fully submerged. Okay? So now this only applies to full submersion, right? Now, I'm going to ask you a question to kind of like verify that you kind of understand what's happening here. So we're going to take two objects and we're going to submerge them. I don't think we did this in the last class. Stop me if we did. I think I did it with my other class though. All right, so we take like, let's say it's a swimming pool. Okay, so we have a very large swimming pool area here to work with to submerge objects in. There's not one that's darker than this. Okay, so we're going to take two objects. One of them is going to be a bowling ball. Now, if you put a bowling ball into a swimming pool, it's obviously going to sink to the bottom, right? So right here we have a bowling ball. And then next to it, we're going to have a beach ball right here. So here we have a beach ball. Now a beach ball, and this beach ball is going to be blown up. It's going to have, you know, it's full of air, right? So if I try to put a beach ball underwater, what's going to happen to it? It's naturally going to float to the top, right? So in order to get this one to stay on the bottom, we'll tie a rope to it. So somehow it's got some kind of hook here or something. And we're going to tie it down to the bottom. So now it's forcibly staying on the bottom due to this rope right here. The bowling ball obviously sinks to the bottom. And what we're going to do here is we're going to say that each is a sphere with the same diameter. Okay. And so this is, I don't want you to answer immediately. I want you to take a second to think about it, and I want everyone to try to answer this. So bowling ball and beach ball, both fully submerged underneath the water. They're each spheres. They have the same diameter. Okay. So here's our bowling ball over here. We'll draw some little holes on it. And the question is, which experiences the larger buoyant force? The beach ball, the bowling ball, neither. They both have the same buoyant force, or there's not enough information. I want you to think about it and then put your answer in the chat, okay? Just think about it, take some time, and then put your answer in the chat. Don't worry whether people write. Just put your answer in the chat, and yeah, we'll go from there. We'll talk about it. Just really, with questions like this, just be honest. Like, put what your first instinct is. What do you actually think? That's what I'm asking you. Like, what's your intuition tell you? It's not important that you get the answer right. Getting a lot of answers, but I really want everybody to try to answer, so I'm going to give you some time. Okay, so it seems like most people have answered, and basically everyone said B or C. Nobody wants to say the beach ball? I'm surprised. Usually, all right, thanks, Keanu. I appreciate that. Usually people say beach ball, but a lot of people said bowling ball. Okay, so it's pretty normal. Usually people say A, B, or C. Those are usually the answers we get. I don't ever see anyone say D, which I could see someone coming up with some argument as to why there's not enough information, but I don't know. So the idea here, and I think Asher Lever kind of puts it correctly, your intuition is that it's B, which is that it's the bowling ball, but C makes sense with the equation, and that's correct. So my intuition when I first saw this question was the answer was the beach ball. That's what my intuition tells me, because you think, oh, beach balls, they float, right? They must have a big buoyant force. But the reality is that both of these objects experience the same buoyant force. And the reason why is because of this. They both have exactly the same volume, because if they're both spheres and they both have the same diameter, then they have exactly the same size, right? That means the volume of the object in this equation right here would be the same for both of them, and that means the buoyant force is the same for both of them, because the density of the fluid and gravity are the same. Now, the only thing that's different between the two of them in terms of the forces in this particular case is just that the bowling ball has a larger weight. And because its weight, well, let's just... How does the bowling ball's weight compare to the buoyant force acting on the bowling ball? Is its weight greater than the buoyant force or less than the buoyant force? It's greater, right? Exactly. So because the weight's greater, it sinks, right? Okay. But the beach ball, it's filled with air, so it has very, very, very little weight, right? Air is an extremely not dense fluid, right? It has about 1/1000th of the density of water. So of course this is going to experience a huge net force upwards, right? Okay. Anyone have any questions? You'll have a pretty good understanding of where buoyancy comes from now and how you calculate it. So the next thing to talk about then is objects that are partially submerged. So let's look at that. So we're still talking about buoyancy. So now, again, we start off with some kind of container, and now we'll just kind of like half fill it. Whoops, I tried to click that to that. Okay, so we have some liquid water in here, and this is the level of the water. And now we're just going to have an object that is floating on the surface of the water. So maybe we've got some object that's floating here. Maybe it's made of wood or something like that. And let's erase this part because that's like the water level. Whoops. Actually, let's not. So we've got this object that's floating, right? And when an object's floating, it's going to have some portion of its volume is going to be below the surface, okay? Right? Some portion of its volume is going to be below the surface. Now, this portion down here is below the surface, right? And what we can do is we can kind of analyze the forces that are acting on this object. And what we're going to look at is we're going to try to calculate the acceleration of this object. So first of all, there's going to be some amount of volume that's beneath the surface. And that volume that's beneath the surface, we're going to call volume displaced. Okay? And what we can say is that the buoyant force acting on this object should be equal to the density of the fluid, of the water, multiplied by the volume of the fluid displaced, oops, and then multiplied by gravity, right? The weight of my object we can write down as the density of the object multiplied by the volume of the object multiplied by g. Do I need to define what I mean by this? Volume with the DISP subscript, I'm saying this is the amount of volume that's displaced. It's the volume that's below the surface. Does that part make sense? Does this equation make sense right here? Okay. Now, someone mentioned earlier, I think they corrected themselves. They said, is this related to F equals ma? Because I think you were looking at this equation and you say, oh, there's a mass and there's a gravity, that's an acceleration. You were thinking F equals ma, right? Okay. Well, now we're actually going to use that equation because now what we can say is with these two forces acting here, right? We've got our buoyant force that's acting up on our object this way, and we've got our weight that's acting downward on our object this way. And how should they be related to each other in this particular case if it's partially floating on top of the water here? They should even out, exactly, right. Like maybe the thing's bobbing up and down in the water or something like that. But these two should be pretty much equal to each other in this case, right? Because in this case, if it's partially submerged, then we can say basically that the net force should be equal to 0, which means that the buoyant force minus the weight should be equal to 0, which means the buoyant force should be equal to the weight. And now we can just equate these two, right? This tells us then that the density of the buoyant force is density of fluid multiplied by the volume displaced, the amount that's beneath the surface, multiplied by gravity should be equal to the weight of the object, which is the density of the object times the volume of the object, right? These two together give you the mass of the object, right? Multiplied by gravity, you get the weight. So this is equal to rho naught, v naught, g. And then we can obviously cancel out a g from each side. And then we get this nice relationship here that tells us how the volume displaced is related to some other quantities. So I'm going to solve it for that quantity right there. So the volume displaced, is our final result from this, is going to be equal to the density of the object divided by the density of the fluid multiplied by the volume of the object. This equation is really only going to work for partial submersion. It's not going to work when the density of the object is greater than the density of the fluid. In fact, you can kind of tell from this that objects that are partially submerged, it has to be the case that the density of the object has to be less than the density of water. Is that clear from this equation right here? Or just from thinking about it? Like, the volume displaced can't be greater than the volume of the object. Would you all agree with that statement? That's not possible. It's not possible that the amount of water that's displaced by the object is greater than the volume of the object, okay? So the left-hand side on this equation always has to be less than the right-hand side. So that means that rho naught, at its most, could be equal to the density of the fluid, right? But it has to be it has to be less than the density of water so that this equation can make some kind of a sense. So to give you a simple example, what's this question here? Is it the volume of the entire object or the part submerged? VO is the volume of the whole object, right? I'll just make that really clear up here because I know that with the zero subscript, sometimes V naught might mean like V initial or something like that. You might think of it that way. But this is the volume of the object. Maybe it really makes more sense when I'm doing this to actually write V and then OBJ down here. Like OBJ is the subscript. That might be a little more clear. But this is the volume of the object. And then VDISP is the amount of the object that's beneath the surface of the water, right? Okay. So, one other thing to look at here is what happens when you push an object underneath the water so that it moves. So the other thing to think about here is suppose that I have a situation where I have something that has a density that is less than water, okay? Or let's say we don't even know. Let's just say we have an object and it's placed underneath the water and we don't know what its density is. We just push it underneath the water and we're gonna see if it floats or if it sinks. Christian Brand asks, so the shape of the object does not matter at all? No, Christian, it does not. It is only the density. The density is the only thing that determines whether an object's gonna float or sink, basically. Christian, that's to answer your question. Okay, so I have some object, right? And I push it underneath the water and I'm gonna let it go, okay? So object with unknown density rho O, that's gonna be the density of the object. And okay, so we have a object with an unknown density, rho naught, it's placed underneath the water. And what we want to calculate is what is its acceleration, okay? So in order to do that, we're going to write down the forces that are acting on this object. We're going to have a buoyant force. We're going to have a weight. We don't know how they're related to each other, so I'm not going to worry about drawing the lines in any particular way. We're going to say then that the net force acting on our object in this case should be equal to the mass of the object times its acceleration. With these two forces, let's first off assume that the buoyant force is bigger than the weight. Okay, let's assume that it has a low density. So then we'll put the buoyant force minus the weight should be equal to the mass of the object times its acceleration. So I'm already kind of assuming, at least with the way I've drawn the equation here, I'm assuming that the acceleration is going to go upwards with the way I've written it. But we can fix that later on for the other possibility. So in this case, we're basically assuming the buoyant force is greater than the weight. That's equal to mass times acceleration. Now what we can do is we can replace the buoyant force in this case, which now, since it's fully underwater, we know what the buoyant force is. It's equal to the density of the fluid times the volume of the object times gravity minus weight is going to be density of the object times the volume of the object multiplied by gravity. And just to keep things the same way on the right-hand side, we can replace mass with density of object times volume of object. Remember, rho v is mass. We're going to use this a bunch in this class, so get really comfortable. When you say density times volume, that is the same thing as mass, right? Rho v equals m. That times the acceleration, okay? So I've replaced buoyant force with density of fluid times volume of object times gravity. Weight, density of object times volume of object times gravity. And on the right-hand side, we have the mass of the object, which is density of the object times volume of the object times acceleration. Does the step going from here to here make sense on all those lines? Does anyone have any questions? So now we can simplify this. Our goal was to find what the acceleration is, right? So solving this equation for acceleration, there's something that's common to every single term, right? Which is the volume of the object, right there, there, and there. There's two g's over here. There's an a right here. So if we divide by rho naught, we'll get that. Acceleration is equal to, what do we have? Rho f minus rho naught divided by rho naught times g. I'm just looking at this equation. Let's make sure it makes sense. I think it makes sense. I think it makes sense. Let's talk about this. So this says, why is acceleration an upward force? It's not a force, Matthew, it's not a force. I didn't draw it. So when I draw free body diagrams, I will draw the forces on the object with a little dot to represent forces, and then I'll use a different color to represent acceleration. It's not a force, Matthew. It's just, that's the direction of the acceleration. And I had to pick something because I wanted to make sure that my equation was like mathematically sensible. Meaning, if I make the assumption that buoyant force is greater than weight, it's going to go up, right? So then I draw the direction of the acceleration, and then I make that direction positive. I guess that's one thing I left off the picture here, is I'm making this direction the positive y direction. Okay. Yeah, no problem. Okay, so let's look at this equation and see if it makes any sense. So this equation says, if I take the density of the fluid, like the density of water, we'll use some examples right here. Let's use the density of water. So let's say that this is a piece of ice. Okay? Is the density of ice less than or greater than water? It's less. Can anyone look it up for me real quick? I think it's like 980 something, but can someone look up the density of ice for me real quick? So let's let the fluid be water, and O is going to be ice. Okay. Is that ice water? Is that liquid? Okay, so 931. So you guys get different answers. And that's normal. You're going to find different answers depending on different things. So we're going to say the density of our object in this case. We're going to say the object is ice. And I'll use the first answer that someone gave. No. We want the one that's in kilogram per meter cubed. So I think it's going to be... Yeah, try to get things in kilogram per meter cubed, if you could, or converted, or whatever. So that last one is really close. 931 kg per meter cubed. Can we use that one? Let me look it up myself and see what I see, because I want to know why you guys are all getting very, very different answers. Yeah, 931 is the first thing that came up for me too, so we'll go with that. So 931 kilogram per meter cubed, we're going to use that, right? Density of fluid, we're going to use 1,000 kilogram per meter cubed. All right. Now let's look at the equation, the way it works out. So we take density of fluid, which is 1,000, okay, minus the density of the object. If it's ice, then that's 931. And then we divide by the density of the object, which is 931. And then we multiply by gravity, so times 9.8 meters per second squared. And I didn't put any units in the thing right here just to go a little more quickly, but why don't I have to write the units in this little parenthesis here? Why did I skip the units there? Because it's a ratio. Exactly. It's the only time it's really okay to not write units is when it's a ratio, because the units don't matter then. As long as they do matter, you need to have everything in the same units, right? Because if I put this in grams per centimeter cubed, yeah, anyway. So we get that equation. We calculate out what that is. And we get a very small number of 0.7 This has to be off screen if I write it over there, so I'm not going to do that. We'll just scroll down a little bit. And we'll write that the acceleration now is going to be equal to 0.73 meters per second squared. Okay, so it's positive. That means it's going to float up, right? And it's kind of small. Now you can test this yourself. Take a glass of water, put a piece of ice into it, right? And then just push the ice down with your finger or something like that, and then let go. The ice, unsurprisingly, is going to float to the top, and it should float to the top rather slowly. And let's mention 2 to 3 sig figs. I'm not really going to talk about sig figs a lot in this class, Troy, especially not during the lecture. But I mean, you know, I'm not going to write a lot of significant figures. I'm usually going to write down, like, during lecture, probably 2, because that way when different people are putting different things in their calculators, they'll usually get the same answer to roughly 2 sig figs. Okay. Had we guessed before buoyant force greater than weight, it would have just been negative. And that's one of the good things about this equation, is it turns out that now if you were to use an object that had a density that was greater than the density of water, right? What would happen to this equation if the density of the object is greater than the fluid density? It will just switch the sign, right? You know what I mean? If we chose something that had a density of 1500, for example, then our answer would have just been negative, right? So this equation kind of tells us what you need to know, is that if the density of your object is less than the density of the fluid, what happens? Does it float, sink, or something else? If the density of the object is less than the density of the fluid, this equation tells us that it does what? If rho O is less than rho F, it will float because it's positive. The opposite would be if the density of the fluid, now let's write it in the same way. If the density of the object is greater than the density of the fluid, let's think something like iron. Iron has a really high density, much higher than water. So it's guaranteed that iron, when placed in water, will sink, right? Not surprising that if you take a piece of metal and put it into water, it will sink. Any metal is going to have a higher density than water, I think. So if the density of the object is greater than the density of the fluid, it will sink. Okay, that's the other, oh, that doesn't look like a word, sink. And then there's a third possibility, which is if the density of the object is equal to the density of the fluid. I can't see, is my face blocking this now? It kind of is. Okay, I think if I scroll down a little bit, it'll be fine. So, get back to where I can see the chat again. I guess if I put the chat like in the middle of the screen, then I could probably notice when, let's do that. That affect where it is on the, move that down a little bit. Okay, apologize. All right, so the third possibility is if the density of the object is equal to the density of the fluid, what's going to happen then? If rho F is equal to rho naught. Partial, that's a good guess. Partial submersion is a good guess. Yep. First thing we notice, as Keanu says, is that the acceleration is equal to 0. Won't it like stay still in the fluid? That's kind of right, Amir. That's basically what's going to happen. So in this case, it's effectively like weightlessness, pretty much. It's pretty much, well, it is weightlessness, right? When your acceleration is equal to 0, that means you don't float, you don't sink, you are what we call neutrally, this is called neutral buoyancy. And, you know, the way that it would work, I guess, is if you were to put this neutrally buoyant object into a fluid, I guess I can use I'll try to draw it as an example. So if you were to place a neutrally buoyant object into a fluid, okay. So let's say we have an object here that's neutrally buoyant. If I were to set it into the water, what Umair is saying, it will like kind of stay still. And it pretty much will. But what would happen if I were to give it a push in this direction? If I put a force on it in this direction here? It's going to have to start moving, right? It can't stay still, right? Now the interesting thing is that when something has no acceleration, right? Then what will happen is it will basically just move. So say instead of saying that I apply a force, because that's going to make things confusing. If I apply a force, it will accelerate. But let's say I apply an impulse. So I just hit it, right? I hit it. it will basically move with constant velocity. In a straight line until it hits a wall or something like that. It'll move with constant velocity. And the cool thing is that, you know, maybe in Physics 1A you saw a demo of, or you talked about uniform velocity. And what's uniform velocity? That's when something's moving with the same speed. Doesn't change, right? You can imagine an object moving across a flat surface with a uniform velocity, right? But it's harder to imagine something moving upwards through water with a constant velocity. But an object with neutral buoyancy could move up through water, down through water, left, right, whatever direction you want to go, and you wouldn't feel really any force other than the drag force from the water. That's all that you would feel, is just the drag force from the water. As far as the buoyant force from the fluid and your weight, they've completely balanced themselves out. So no matter how you move your body, it doesn't really matter if you are this object, sorry, then you would move with constant velocity. I think that's pretty fascinating. It's a way to achieve, effectively, weightlessness, which would only really exist kind of in space, right? In space, you would also feel weightlessness, right? So it's kind of the same idea if you're like in outer space, and you're wearing like a spacesuit. Very similar type of effects here, except that you're surrounded by a fluid, so there is a drag force, but other than that, that's what neutral buoyancy means. I think I asked before, and I guess I'll ask again. Does anyone here do any kind of scuba diving? Or even scuba diving training of any kind? I think no one really answered last time, and that's fine. I also haven't been scuba diving before. But what I do know, because I have family members that do this, and because I've had students before that tell me about it, is that scuba divers will use a belt that they put on. So think about a scuba diver. When they get in the water, what do they have to have? They have to have a big tank of air, right? A big tank of oxygen so they can breathe. Oxygen, even if it's compressed, is going to have a lower density than water, right? So when you get into the water with your oxygen tank on and your goggles and your suit and stuff like that, probably you're going to tend to float, right? Would you all agree? Probably if you jump into water with it, you're probably going to float, right? Oh, you went saying you did do scuba diving once. So it's going to be difficult if you're naturally buoyant with your scuba tank on. It's going to be very difficult to go under the water. Is that correct? Those of you that have been scuba diving? And you have to use like a belt that has weights on it to help you to get underneath the water. Is that accurate? Yeah, so Troy's saying the diving belt needs to be like 5% of your body weight. Yeah, okay. Now, in addition to this, because you use some kind of a belt that has the ability to modify how much weight it has on it, right? Like you can add or remove weight. So what you can do is you can intentionally make it, by adding on different attachments, you add more and more weight until you reach neutral buoyancy, right? And that's the goal. If you're neutrally buoyant in your scuba, with all your scuba gear on and stuff like that, then you know you've got your flippers on, right? You hit your flippers just a little bit, and you just cruise through the water as if you're just in outer space or something like that. Isn't that cool? You can basically like move around in the water like an astronaut would in space, just by attaching just the right amount of weight, so you reach the point when your density, right, is exactly the same as the density of water, and then you're literally swimming around in water as if you were like a blob of water, pretty much, unaffected by the, yeah. Anyway, so I think that's really neat. I need to go scuba diving. Maybe I can experience this, and sounds neat. All right, so I think we do a problem, and then we're going to do another. We're going to do a problem, and then we're going to do a quick quiz, and then we're going to do another problem. Actually, this is the easiest problem. So let's start off with this one. We'll do this one, and then that one, and then we'll do this question. Okay, so here's the first question we want to do. Okay, this one's related to partial submersion. So I'll go ahead and grab this equation. Let me highlight this real quick and just say that, whoops, that's not what I wanted to do. So let's just say real quick. This equation was for partial submersion. This is when an object is floating on top of the surface of water. Okay. All right. So here's a problem that deals with partial submersion. So let's take that equation and copy it down here. All right, so it says an iceberg floating in seawater, as shown in this figure, is extremely dangerous because most of the ice is below the surface. So here's a picture over here where it's an iceberg, and it doesn't look super large in this picture, even though I suspect that's still a pretty big iceberg. Looks like a mountain coming out of the water. And here's a side kind of animation or cartoon of it, which shows that a significant portion of the iceberg is actually beneath the surface. Okay. So it says, an iceberg floating in seawater is extremely dangerous because most of the ice is below the surface. This hidden ice can damage a ship that is still a considerable distance away from the visible ice. So you can see in this picture, even though the ship isn't actually touching the iceberg, the hull of the ship is actually going to come into contact with the piece that's underneath and perhaps topple the ship. And I guess this is how the Titanic sunk long, long ago. Okay, so the question is, what fraction of the iceberg lies below the water level? What fraction of the iceberg lies below the water level? Okay, that is to say, how much is here? All right, so on our picture, let's draw a little line right here, because that's the surface of the fluid, and just say that all of this stuff down here is the volume of water that's been displaced by the portion of the iceberg that's beneath the surface, right? That's all this stuff down here, not including the part that's out of the water. And our goal is to figure out what fraction of the total iceberg volume is down here, right? So to find that fraction, what kind of ratio should I take? It's not one step before that, Troy. This problem has like, it's a really short problem, so I'm trying to like go as slow as I can, because otherwise it's just gonna look like, what does this mean? The fraction below the water level. What does that mean? You're not wrong, Troy. That's what the answer is. The answer is gonna be related to that ratio. But my question is, when you read these words, fraction below the water level, how do I turn that into a usable piece of information? You know what I mean? How do I turn that into a mathematical statement of what we're calculating? What are we calculating in terms of these variables when we say fraction below water level? We're going to try to calculate the volume displaced. Yeah, but it's a fraction, right? So it's the volume displaced over what? It's the ratio of the volumes. Thank you. That's right. Yeah. So this is what we mean when we say the fraction below the water level. That is, take the volume that's below the water, divide by the total volume of the object, right? That's the fraction. Does everyone agree that this is what that means? This is the hardest part about physics problems, really, is just getting started. Because once we know what we need to do, it's really easy. As long as we know that we need to do this, and we recognize that this is a partial submersion problem, where an object is floating on top of the surface, and we go back and we say, how do I do partial submersion? This is partial submersion. Well, then it's really simple, because this equation tells us that in order to find this relationship, this is also equal to, as I think it was Troy that said, this is exactly going to be equal to the density of the object divided by the density of the fluid. Did I get that ratio right? I must have, because I copy-pasted it. Yeah, object over fluid. It has to be the way it is, because otherwise it's not floating. Now, what are we going to use for the density of the object and the density of the fluid? What is the fluid in this case? It's seawater, right? So we need the density of seawater. Oops. Do you all think seawater is more dense or less dense than normal water? Yeah, technically we would need cold seawater, he's right. It's more dense, right? Why is it more dense? Well, there's a lot of like salts and things like this. And in case you didn't know, it's easier to float in seawater or the ocean than it is to float in a pool, because the density of the water is greater, which means that there's a higher probability that it's greater than your body's density. So that's why they say it is easier to float in the ocean, and it's true. Okay, so we need that. Maybe you all can look that up. And then for the density of the object, we need the density of sea ice, right? Of seawater ice. I don't know if we can find this. So those are the two things that we need. So I got 1036 as some kind of an average. It actually depends on the temperature. So this is at 3.5 degrees Celsius. So this one is going to be 1036 kilograms per meter cubed. And then if we do sea ice density, see 917 is what I found. Here we go. Density of glacier ice. Let's use that. So this is 916.7 kg per meter cubed. So that's rho O. Okay, so what's the ratio then going to be? It's going to be 916.7 divided by 1036. Again, same units, so that means that the fraction is equal to this ratio. So you're obviously going to get a different answer depending on what numbers you put in here, but you should always get a number that's greater than like 85%, I think, depending on what numbers you pick. So it's 88%. So almost 90% of the volume of the iceberg is below the surface. That number is really high, right? I was really surprised the first time I did this calculation. I mean, it's not too surprising once you know what's going on. Once you understand that you're just doing a density of fluids ratio, and you know that the density of ice is really not that much less than the density of water, since they're both similar substances, obviously, the same substance. But they're so close together that it makes it so that a huge, huge portion is beneath the surface. Think about something like wood. You know, when wood floats on top of water, there's usually a much larger fraction that's above the surface. So it's kind of surprising how much is beneath the surface. Okay, simple little problem to understand how you do little calculations like this. These kind of calculations are going to show up from time to time in problems that you do. It might not be the whole problem of what you do, but you will have to do it from time to time. Anyone have any questions? It's a pretty straightforward problem, but if you do have questions, let me know. Or just general questions about what we're talking about here. See some people typing. I'm going to go ahead and get the next part set up. Okay, we did this. We're next going to do these two. I guess what we'll do is we'll do this first. Yeah. Yeah, you'll know the densities on the test. I'll give those to you. I probably am not going to specify density of water. You just kind of have to memorize that one. Okay. All right. So let's do this problem. This is another conceptual question, and it's kind of tricky, so I'll give you a little bit of time to think about this. So do not answer until I ask for your answers, okay? I'm probably going to give you several minutes to think about this. So we're going to read this together, we're going to draw a picture, and we'll talk about it, and then I'm going to give you some time to think about the answer. Do not put your answer too soon, though, okay? Because I know the moment you put an answer in, it's going to kind of affect other people. All right, so this is the question. It says, can everyone read this okay? It's pretty big. Hopefully you can. It says, you are shipwrecked and floating in the middle of the ocean on a raft. Your cargo on the raft includes a treasure chest full of gold that you found before your ship sank, and the raft is just barely afloat. So you're barely floating. In order to keep you floating as high as possible in the water, should you leave the treasure chest on top of the raft, B, secure the treasure chest to the underside of the raft, Or C, hang the treasure chest in the water with a rope attached to the raft, and assume that throwing the treasure chest overboard is not an option you wish to consider. All right, so this problem conceptually, I think, sets you up pretty well for one of the the lab manual problems that you have to do, because it kind of hints at some of the ideas you need to think about. Okay, so we've got this person, they're on a raft, and it says you have a treasure chest, and it says the raft is just barely afloat. So I'm going to take that to mean that the raft is just like, only a little bit of the raft is actually above the surface of the water, okay? So you're just about to sink. You're almost like the same problem that we just did a second ago. It's similar to the iceberg in the sense that just your raft is just barely above the water. Here's your raft. Sitting on top of the raft is a treasure chest. So we'll draw a treasure chest right here. And obviously you're on top of the raft too. So you're sitting here on the raft. And with all these things together, the raft is just barely floating. If you added a little bit more weight, it would start to sink, okay? So the question is, to keep you floating as high as possible in the water, should you leave the treasure chest on top of the raft? Should you take the treasure chest and tie it to the bottom? Should you hang the treasure chest in the water with a rope attached to the raft? So you basically would, yeah. So what's A? This is A, right? B would be, let's do some. Okay, so there's 3 different possibilities. We've got A. So this is A, this is B, and this is going to be C. So for B, what we're going to do is we're going to take the treasure chest. Now, I'm not going to change what happens to the raft. Like, meaning I'm not going to tell you in advance if this makes the raft go up or down, so you have to think about it yourself. Okay? All we know is the initial scenario here, that this is accurate, that this is where the water is right here. So we attach it to the bottom here, and the other possibility is we tie it to the bottom. There's 3 possibilities, and those are the possibilities. Whoops, that's not what I meant to do. So we get a rope, and we tie it here. And in this case, I don't know, we tape it to the bottom. Who knows how this happens, but somehow it's attached to the bottom here. Maybe we tie a rope or something on this and then to here. That's the only way I think we can do this, maybe. Maybe we like tie a rope like that or something like that, I don't know. But it's attached somehow to the bottom of the raft and it's not falling off. So which of these 3 options, how does it ask it? You're shipwrecked, your cargo in the raft includes a treasure chest, the raft is just barely afloat. The question is, to keep you floating as high as possible in the water, which of these should you do? Which of these 3 options will have you floating the highest in the water? Okay, so don't answer immediately. I want you to take a minute or 2, think about it, and then I'll ask for your answers after a minute or 2. You can ask any question you want in the chat. You can also, open your mic and ask a question if you want to as well. Oh, I guess one other thing I should do to make this more fair. Let's assume we put it right in the middle so that there's no, because I just looking at this, I realized you might think, oh, if you tie it on the side, well, then it's going to sink. So let's assume we put it right in the middle in all cases. Okay, that was actually 3 minutes, so I hope that was enough time. Okay, I want you all to do something for me. I want you to don't push enter, but just type your answer into the chat window. Like, put your answer in, and then I'll tell you all to push enter at the same time. So just put your answer there, but don't push enter. Okay? I'll give you a couple seconds. Okay, so at the same time, in 3, 2, 1, push enter now. Oh, look at that. That was awesome. You guys all answered, too. That was really good. Okay. There's a lot of different answers. Whoops. Okay. Oh, there we go. Okay, let's scroll back up. So a lot of B's, a lot of C's, some A. This is great. So this is really good when you get all these different answers. I like this. Okay, so I see a lot of B's. I see one person said C. And I see some A's. So it's a pretty good mix between A's and B's, and I see one C. Okay. So, I'm not going to tell you the answer is right. I kind of want to hear your arguments. If you said A, why did you choose A? You want to argue for A? Probably a little easier if you just open your mic and say what you thought, if you're confident enough. It's okay if you aren't. And I guess likewise, just to make things go a little more quickly here, if you typed B, type why you typed B, and if you typed C, type why you typed C. Or say, either, whatever you want to do. Why did you choose those? Okay, Christian says, I chose B because I think that if the most dense part is submerged, then more will be above the water because it's less dense. Okay. I think you're on the little bit of the right track when you say the more dense part submerged. Richard chose A because the gold is more dense than water, so if we were to place it on the underside or attach to the rope, the weight would overpower the buoyancy force. Okay. Okay. Astrolover says, I typed B because I figured in scenario A the chest wouldn't have a buoyant force, or maybe it would be only the weight of the chest instead of a buoyant force. Ah, see, this is Astrolover. That's a very good explanation. That is a very good explanation. Richard's very close to that answer. Richard's definitely indicating the issues with that. And then Troy says he chose B because for C, the buoyant force would just loosen the rope and slow down the raft once it moves and tightens the rope. Keanu says C or B. I feel like the chest is submerged. The buoyant force helps reduce the raft sinking. Okay. So both Keanu and Astrolover, you both have hit upon the main ideas that matter. And Christian, you're really close. The main point here is, I believe the correct answer is B or C, and we can go look it up. This is not from your textbook, but I can pull up the textbook here in a second. I believe the correct answer is B or C. And the reason why, as was said, we'll use Keanu's words, if the chest is submerged, the buoyancy helps reduce the raft sinking. Now look, everything is already floating, right? So the question would be, how can we make ourselves float higher? And the answer is, the moment you put the chest underneath the water, the chest now has more forces. Let's actually just look at the forces that are acting on the raft and everything in both cases. In the first case, you have the mass of the person, or the weight of the person is basically acting on the raft, right? That's the same in both cases, so we don't really need to even consider that. That's not going to change, right? Likewise, the force of weight on the raft and the buoyant force on the raft, those aren't going to change either. So really, all we have to figure out is what kind of forces are acting kind of on the weight, on the gold. Now, in this particular case, the only force acting is going to be the weight, right? But the moment that you put it underneath the water, even though the weight is going to be significantly higher because it's made as it's a treasure chest, right? There's still going to be a tiny buoyant force acting upward on the chest as well. And that tiny buoyant force is going to mean, when you compare this to this, that, think about it like this, the apparent weight of the chest has now gone down. I don't think there's any difference between the two of these, except that C is more logical, in the sense that how are you actually going to attach a treasure chest to a raft, right? Does the raft just have natural hooks underneath here that you're just going to attach the chest to? I mean, maybe. But having a rope on a raft is reasonable, and using that rope to tie something underneath, this is reasonable, I think. So maybe C is the best answer, but these are both, B or C are both correct. So if you answer B or C, you got it right. If you answered A, I understand. The whole point of these questions is to test our intuition and not to test our knowledge. And by testing our intuition, you can question your intuition and then learn to develop a new idea of what's going on. So in this case, what's going on is by putting the chest underwater, you add an extra upward force that wasn't there before, and that reduces the apparent weight of the chest, which then allows you to float a little bit higher. Okay, so I think that's a good problem. I hope you all found that interesting too. I'm glad to see you all interacting and good answers and good explanations that everyone gave. So I said we would stop at 10:50. We went a little bit longer, so we'll take a break until 11:05, when we'll come back and we will do a couple more problems. So let's stop the recording. I don't ever remember starting the recording. Let's hope that it's actually started. Yeah, it did. Okay.